Welcome back. In this video, we'll discuss strong induction. So the question is, what is the difference between mathematical induction and strong induction? And the truth is they're equivalent, and we'll take a look at what that means. We will explore this topic by first looking at strong induction, the definition of what it means, and what the basis and inductive steps are to carry out strong induction. And then we'll look at some example proofs using strong induction, and finally take a look at one application within computer science, so the use of strong induction in computational geometry. When we explored mathematical induction, we used the model of an infinite ladder. And what we said was that the form of mathematical induction is that you first show that you can reach that first rung wherever it begins. And then you show that if you can reach one rung of this ladder, you can reach the next ones. So reaching rung K implies that you can also reach rung K plus 1. So that was the big idea behind mathematical induction. So what is the bigger idea behind strong induction? This is over the same domain. So we'll consider a scenario where you've got a tree house, you've got a ladder to a tree house, and the ladder is infinitely long, but it starts off at some height. And so the first hurdle is to make sure that you can reach that first rung. And this is the same as in mathematical induction. So first we have to show that we can reach that first rung. The second step of mathematical induction is to show that if we can reach every rung up to a specific rung K, then this tells us that we can reach the next rung. So showing that if we can reach all the lower rungs, we can reach the rung that follows, K plus 1. Seems similar, but the difference is based on that inductive hypothesis. This time around, we're going to assume that we can reach everything from that base rung all the way up to rung K. And that's a bit more to play with in our tool belt. So what this looks like is if we define a propositional statement, P of n, and in this case, P of n, we're going to set to be we can reach rung n. And this is something that has a truth value. We can either reach rung n or we can't reach rung n. So the first thing we have to show is that we can reach the base rung. So whatever that lowest rung is, we can reach it. The next step is that we show that if we assume we can reach every rung from rung B all the way up to rung K, then we can conclude if that's true, then we can reach the next rung. And if these two are put together, then we have everything we need to say, do you know what? We can reach every rung of this ladder. And let's step through what this means to show that this is true. So that the first step was defining the propositional statement P of n. And that's really important. Sometimes it's hard to tease out within a problem what your propositional statement is. So in this case, we're going to let P of n be we can reach rung n of our infinite ladder. The next step is to show that we can at least get to that first rung. And this is the same as with mathematical induction. We have to show that we can reach that base rung. That means we have to show, if we're showing that something is true over all the integers greater than or equal to b, then we have to show that P of b is true. Next is our inductive step. And our inductive step is where we assume that we can reach every rung from rung B to rung K. And then we show that if we can reach those, then we can reach the rung above all of those, P of K plus 1. And so this means that we start with this assumption that P of B and P of B plus 1 and P of B plus 2 all the way up to P of K are true. And that's our inductive hypothesis. So this is the piece that differs from mathematical induction or weak induction. And the piece that we want to show, though, is the same. So This is very similar to standard weak induction, but it has that one extra step. So strong induction, put it all together. The basis step, we show that P of B is true. The inductive step, we show that reaching the ability to reach rungs B through K shows that we can reach the rung above this, rung K plus 1. Let's take a look at another ladder climbing example. Suppose we can reach the first and the second rungs of an infinite ladder. And we also know that if we can reach a rung, then we can reach 2 rungs higher. So if we assume that we use the same P of n, which is that we can reach rung n, so a propositional statement P of n is that we can reach rung n, then what this tells us is that we are given the fact that we can reach rung 1, we can reach rung 2, and if we can reach rung K, then we can reach rung K plus 2. So which form of induction will work? Can we use weak induction? Mathematical induction that only lets us know that we can reach that base, and then if we assume P of K, we must show P of K plus 1? This doesn't feel like that's enough information. There's no clear way to move forward with that inductive step. I can show that I can reach 2 rungs higher. If I can reach a rung K, I can reach the rung 2 higher. But I don't have a clean way to show that if I can reach one rung, I can reach the next rung. So maybe that's not the best approach. And in fact, this is a great candidate for strong induction. So now we've already defined that propositional statement P of n, and that is that we can reach rung n. So our inductive step is to show that P of 1 holds. We can reach rung 1. But we remember that we've been given the following. We've been given that we can reach rung 1, we can reach rung 2, and if we can reach a rung J, then this tells us that we can reach J plus 2. So P of 1, that's done for us. That was given. Our inductive hypothesis in this scenario is that we can reach rungs 1 through rung K, whatever K may be. And then for all K, we want to show that we can reach rung K plus 1 under that assumption. So what that looks like, well, when we want to show this is true for K greater than or equal to 1. If K equals 1, then what we need to show is that P of 1 implies P of 2. But this is done as well because we know P of 2 holds. That was given. And so this is done. If we have K greater than or equal to 2, we have a nice little trick because P of K minus 1 holds by our inductive hypothesis. And if we have that, then we know that if we can reach a rung, so P of K minus 1, then this implies that we can reach a rung 2 greater. And so that means that we can reach rung P of K minus 1 plus 2, which is equivalent to saying we can reach rung K plus 1. And that means we have everything we need to show that we can make it all the way to the top of this ladder. So how do I choose between strong and weak induction? Which should we use? And when would you want to use it? So we can always use strong induction. This is always a possibility instead of using mathematical induction. But there is no reason to use it if it is simpler to use mathematical induction. Why can we always use strong induction? We won't go over the proof, but weak and strong induction, they're equivalent. In fact, strong induction is called the second principle of mathematical induction, where weak induction is that principle of mathematical induction. So my approach, take a look at the problem, decide if you can if there's a straightforward approach using mathematical induction. If there's not, then apply strong induction. When in doubt, strong induction will help you out. Let's look at another example. Let's show that if n is an integer greater than 1, so n is in z greater than 1, then n can be written as the product of primes. And what's the motivation for this? Well, this is the fundamental theorem of arithmetic. This is something we can get behind. You've likely seen that numbers can be broken down into their factors, their prime factors. So this 6 can be written as 2 times 3. 15 can be written as 3 times 5. You can always break these down into their prime factors. Well, while we take that as fact, because this is the fundamental theorem of arithmetic that we've learned from a young age, this had to be proven at some point in time. And the easiest way to prove something like this is to use strong induction. And the reason for that is this. If I go backwards and think about what I would do with 16, if I know that 15 can be written as a product of primes, and I know that our base case, in this case, it's everything greater than 1, so our base is 2. 2 can be written as the product of primes. Is that information enough to take me to 16 being a product of primes? I don't even know how to make use of that information because I don't know what the primes are that make up the previous number. If I'm looking at a number k, I'm not sure what those numbers are. I can just assume that they can be written as a product of primes. But there's a parity shift from k to k plus 1. So I already know that I might be gaining or taking away a 2. How can I make use of that as I move forward? I don't know. So this would push me to move forward with strong induction. So our propositional statement is that n can be written as a product of primes, and our basis step is to show that this is true for 2. 2 can be written as the product of primes. We know that 2 is a prime number, and so 2 can be written as the product of 1 prime itself, 2. So the inductive step is that we're going to assume that the numbers 2 all the way up to k can be written as the product of primes. And then we have to decide what we want to show. We want to show that k plus 1 can also be written as a product of primes if that assumption is true. So what does that look like? I would say that we break it down into 2 cases. Either k plus 1 is prime or k plus 1 is composite. If k plus 1 is prime, we are done because we can write that out as the product of 1 prime, k plus 1. If k plus 1 is composite, then I know that there is a factor other than 1 and k plus 1 itself. So that means that I can express k plus 1 as a times some other number b. And if I assume that a is at most as big as b, so b is equal to or greater than a, then I can say I know that because it's a factor that's smaller than k plus 1, then these are at most k. And because it's bigger than 1, it's something other than 1 and itself, both a and b are bigger than or equal to 2. So now, something I note is that any number between 2 and k, well, that falls under our inductive hypothesis. Since both a and b are between 2 and k, then p of a holds and p of b holds. And this is interesting because now we know that a can be written as a product of primes and b can be written as a product of primes. And if that's the case, then we can also write k plus 1 as the product of primes. Okay. Our final piece is to look at a CS connection. So how does this all come back to computer science, and how do we use it aside from program correctness and algorithm verification? The other place that we see this is in proofs looking at how we can do things in computational geometry. Computational geometry is used in computer graphics, computer games, robotics, so many different areas, and it's an interesting area to explore. So one basic operation of computational geometry would be splitting up simple polygons into smaller, simpler steps. So how would we divide a simple polygon, such as the one on the screen, into triangles? Well, we can add these non-intersecting diagonals and cut it up into different pieces until we make a number of triangles. But how many will we make? What does this look like? Can we always do it? And in fact, there's a proof using strong induction that can show that no matter what this n-sided simple polygon looks like, if there's greater than or equal to 3 sides, so a triangle or any other simple polygon with n sides, it can be triangulated, so cut into triangles using n minus 2, exactly n minus 2 triangles. And so this is quite interesting when you think about what that would be. So using non-intersecting diagonals, what I can do is I can make n minus 2 triangles exactly. So maybe my first one is to look something like this. You can see that I've got 1, 2, 3, 4, 5 triangles. But I could just have easily have done something slightly different. And that is, I could have cut all of this up in a very different way. So again, I have 1, 2, 3, 4, 5 distinct triangles. You might ask yourself, well, what does this have to do with anything that I might do in computer science? But proof of this has implications for computer graphics in big ways. Oftentimes, we might want to render something, a three-dimensional object, and the act of rendering that object, it's computationally heavy. And so what we can do instead is simplify these complex real-world surfaces by representing them as a series of triangles. And so instead of just rendering that 3D object as one whole, we can break it down and decompose it into these smaller triangular surfaces and render those individually. And this is just one way that induction has served a purpose to computer science. That's all for now.
Can we look at some more?
What?
Can we look at some more?
What?
Can we look at some more?
What?
Can we look at some more, please?
Next time we will look at some more, and we'll look at the repetitive nature of recursion algorithms and structural induction. See you next time.
Thanks for watching.